Alright, so now we're going to go over some of these properties and nomenclature as they relate to amines. In this first section we're doing nomenclature, and we're going to have a mix of both common names as well as IUPAC names. So for one like Part A, where the groups are very, very simple, that's definitely an example where we're going to be using common names. Because what's attached here to the nitrogen? It's 3 methyl groups. And so we just call that trimethylamine. In Part B, we have 2 ethyls, and we have 1 isopropyl. And so we could call this diethyl isopropyl amine. And in general for amines, if a common name like this is available, that's almost always what we're going to be using. Now Part C is a little more complex. We have a methyl, an ethyl, and a propyl. And with 3 different groups, we don't usually use common names. So we would use the longest one, say propanamine, and we number it starting at the amine end, so 1 propanamine, and then we'd have N-ethyl, N-methyl. That tells us we have a methyl that's attached to the nitrogen, as well as an ethyl that's attached to the nitrogen. Part D, just 2 ethyl groups again, diethylamine, Part E, ethyl and methyl. So again, we would use the common name with just 2 very simple groups. In Part F, you could go either way. So we have 8 carbons. So we could call it octylamine, or we could use the more formal name of 1-octanamine. Is one better than the other? Not necessarily, not in a case like this. Both of them fully communicate what the name of the compound is. Part G, we have an isopropyl group, a propyl, and a butyl. Again, with 3 different groups, we're going to use the more formal name. So we use 1-butanamine as the parent, and then we would call it N-isopropyl, N-propyl. In question 2, we want to rank compounds from lowest to highest boiling point. Remember, this is generally based on the intermolecular forces. Our cyclohexane molecule in the middle is going to be the lowest. It has no forces other than van der Waals attraction. The other 2, the amine and the alcohol, both have hydrogen bonding. But we know because of the bigger electronegativity difference in the alcohol that the alcohol has stronger hydrogen bonding and therefore stronger attraction and a higher boiling point than the amine does. In Part B, again we have an ether here which largely only has van der Waals forces. We have the amine which has hydrogen bonding, and then we have the carboxylic acid which has both stronger hydrogen bonding as well as the dipole-dipole interaction from the carbonyl. Finally, here in part C, we have 3 primary amines. So they all have pretty similar hydrogen bonding. So what makes the difference here is the length of the carbon chain. The longer the carbon chain, the stronger the attraction and the higher the boiling point. In 3, we're looking for water-soluble molecules. We can immediately rule out this one. With no NH bonds, here, no hydrogen bonding, not water-soluble. Otherwise, it's very much like other functional groups, under 4 carbons, and we're very likely to be water-soluble, over 4 carbons, and very unlikely to be water-soluble. Finally, in question 4, strongest base in each pair. Part A, it's the one with 2 ethyl groups. Remember, when we're talking about acids, electron withdrawing groups give us stronger acids. So with bases, it's the opposite. Electron donating groups give us stronger acids. And so same thing in part D, extra carbons, more donation, stronger acid. Now in B and C, what we have are the addition of double bonds. Double bonds, especially aromatic rings, are in general electron donating. Electron withdrawing when they're next to amines. And so having extra aromatic rings, extra double bonds next to an amine actually helps to pull electron density away from the nitrogen. And so we get stronger bases for these two that don't have that next to them.